Hi there, this is Heath. We're looking at the second day of notes in this course. This is Computation in Z mod N. Let's go ahead and get started. So when we're talking about the integers mod N, we're talking about the set of integers that runs from 0 up through n minus 1, where then when we get to n, we wrap around and go back to 0 again. That is, we're creating equivalence classes where two integers are equivalent if n divides their difference. For example, in Z mod 5, the integers 3 and 38 are equivalent because 38 minus 3 is a multiple of 5. Or another way of thinking about this is, if we write all this out, 16, 17, 18, 19, I'm going to just skip ahead, 35, 36, 37, 38, 39. 3 and 38 are equivalent because they end up in the same column if we wrap around every 5. So 7 and 12 are equivalent, 14 and 39 are equivalent, 10 and 35 are equivalent, so on and so forth. Two numbers are equivalent if their difference is exactly a multiple of 5. Depending on which classes you've taken before, you may have seen some formal notation to distinguish an integer class, which is an entire column of this table, from an individual number, so that the square brackets around a 3 indicates the 3 column. But we're going to avoid the formalism in this class. If I write something in Z mod 5 and I just write a 3, it could represent any number in the 3 column. Okay? All right. So we can add, subtract, or multiply over Z mod N. For example, in Z mod 26, 4 times 6 is 24. 24 plus 3 is 27. 27 and 1 are in the same column, so that they're equivalent mod 26. But we cannot divide in Z mod N because we're working in a set of integers, and the quotient of two integers, like 3 over 7, may not be an integer. And so division is not allowed. It's not allowed in Z mod N. So we'll have to talk about how do we compensate for not being able to divide in this system. And we'll talk about that in a moment. So let's try solving a couple of congruences. 7 times x is congruent to 3 mod 10. So we could do this by brute force. Try every column. 7 times 0 is 0. 7 times 1 is 7. 7 times 2 is 14, which is equivalent to 4. 7 times 3 is 21, which is equivalent to 1. 7 times 4 is 28, which is equivalent to 8. 7 times 5 is 35, which is equivalent to 5. So on and so forth. After some point, you get kind of tired of doing this, but you get to the very end, and 7 times 9 is 63, and that's congruent to 3. And so x turns out to be 9. Now, there's a couple of ways we could speed that up. I'm looking for the answer that gives me 3, but once I find the answer that gives me 1, that 7 times 3 gives me 1, then I could multiply both sides by 3, and then on the left side I'll have 7 times 9, and on the right hand side I'll have 1 times 3. And so I could skip ahead from 1 to 3. As soon as I find the answer that gives me 1, I can then use that I can leverage that to find the answer that gives me 3. And so I didn't have to do this entirely by brute force. I could have gone as far as just this row, and once I recognized that I had a 1, I could use that to get to a 3. Okay? All right, let's try another example. Let's solve this congruence. 8x is congruent to 5 mod 12. So if we try this, 8 times 0 is 0. 8 times 1 is 8. 8 times 2 is 16. Well, 16 is bigger than 12, but that's congruent to 4. 8 times 3 is 24, and that's congruent to 0 again. 8 times 4 is 32, and that's congruent to 8. And I'm starting to see this pattern. I'm just getting 0, 8, and 4, and then a light bulb comes off. So I see this repeating pattern. And then the little light bulb comes off. And I notice that 8 times x is always going to be even. And even if I subtract 12 because I've overflowed my result, like 16 or 24, subtracting 12 will not make it odd. And so there's no way that I can get a 5 for an answer. This congruence has no solution. And it had to do with the fact that 8 was an even number, and then 12 was also even. And so as soon as I've multiplied by 8 and then subtracted 12, I can't ever get myself back to an odd number as an answer. So this congruence has no solution. Let's try one more. There are 3 congruences in this example. 3x is congruent to 0 mod 9. Well, one answer is pretty easy. 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. And since we're in mod 9, 9 is also congruent to 0. And then I start to see this pattern again. 3 times 4 is 12. 12 mod 9 is 3. 3 times 5 is 15. And 15 mod 9 is 6. And I'm starting to see 0, 3, 6, 0, 3, 6, 0, 3, 6. And so I would guess that 3 times 6 is going to be the start of another 0. And it is. 3 times 6 is 18, and 18 mod 9 is 0. 3 times 7 is 21. That's a 3 again. 3 times 8 is 24, and that's a 6 again. Why don't I want to do 3 times 9? Because 9 in the system is the same as 0, and I've already done 0. And so I stop. And so this solution, or this congruence, has 3 solutions. X is equal to 0, x is equal to 3, and x is equal to 6. So what I want to ask at this point is, can we make a conjecture about whether a congruence is solvable or not? That this one had one solution. This one had no solutions. This one had 3 solutions. And if I call this number A, and this number B, and this number C, one of the things that we notice is that if A and C have a common factor, that affects what kinds of things we can achieve. For example, 8 and 12 both have a factor of 2, which means 8 times anything is going to be even. Subtracting 12 makes it still be even. And if B is not even, then we have no solutions. So if A and C have a common factor, but B does not, then we have no solutions. What about this example here? A and C also have a factor in common. It has a factor of 3 in common. Does 3 divide evenly into 0? The answer is yes, because 0 and 9 are equivalent to each other. And so 3 times 3 is 0, which means 3 times 3 is, or 3 times 3 is 9, which means 3 times 3 is 0. And so there is a multiple of 3 that equals 0. And so if all 3 have a common factor, and I should, I guess, say have a common factor that's not 1. Any two integers have 1 as a common factor. Domp, domp, that doesn't really tell me anything. If all 3 have a common factor that's not 1, then we might have many solutions. That's what it looks like based on this example. What happened here, though, is that 7 and 10 don't have a common factor except for 1. And so I couldn't come up with a pattern like this only generates even numbers. Or this only generates multiples of 5. This turned out to generate all of the numbers. In fact, we got through all of them by the time we got to 3. And so if A and C have no common factors, except 1, then we get one solution. So let's look at this on the next slide and see if this makes sense here. GCD and Solving Congruences. This is a theorem in the book. The congruence AX is congruent to B mod n has a unique solution in Z mod n. That's what unique means, exactly 1. If and only if the GCD of A and n is equal to 1. This means greatest common divisor. And if 1 is the greatest common divisor, then there can't be any common factors that are bigger than 1. Okay? So this is a theorem in the book. We're not going to take the time today to prove the theorem, but we now know how to tell whether we're going to have a unique solution or not. We're not going to take the time today to prove this. Okay? What happens if the GCD is not equal to 1? Then the congruence either does not have a unique solution, it does not have a unique solution, and that means it will either have no solution or it will have multiple solutions. And that has to do with based on what that other number turns out to be. Okay? All right. So if the GCD of A and n is equal to 1, then we say that A and n are relatively prime. This is just a term that we use to say that these two numbers are equal to, that they have no common factors except for 1. So If and only if GCD is of A and N is equal to 1, then A has a multiplicative inverse, which we can use to solve congruences. So a multiplicative inverse, let's push this down a little bit further here. Multiplicative inverse of A mod n is a number A inverse such that A times A inverse is equal to 1. We just saw from the theorem that this congruence can be solved. I should say, instead of equal to 1, is congruent to 1 mod n. Might not be equal to 1, it might be equal to something that's in the same column as 1. But that's okay. Okay? So in Z mod 26, the inverse of 9 is 3, because 9 times 3 is 27, and 27 is congruent to 1 mod 26. And so if I want to solve a congruence involving a 9 on the left side, I can multiply both sides by 3. 9x is equal to 14. 3 times 9x is 3 times 14. 3 times 9 is 27. 3 times 14 is 42. But 27 is the same thing as 1. So on the left side, we just get 1x. And 42 is the same thing as 16, because we're working on 26. That is, the 3 and the 9 give me a number that, because it's in the same column as 1, it cancels out and gives me 1 on the left side, and then this gives me 16 on the right side. Okay? So this is our idea. We can't solve this by not dividing. We can't divide by 9 and get x equals 14 ninths, because 14 ninths is not in integers. Instead, we multiply by 3, because 9 times 3 gives me a number that is equivalent to 1. And that's the important thing. And so it makes the number in front of the x go away. All right? So we always have a multiplicative inverse if the two numbers are relatively prime, which means their GCD is equal to 1. And we have two algorithms that help us determine the multiplicative inverse of an integer modulo another integer. One is called the Euclidean algorithm, and one is called the extended Euclidean algorithm. The Euclidean algorithm is what verifies that the GCD is equal to 1. It checks to make sure that the GCD is equal to 1, and then the extended Euclidean algorithm gives us the correct multiplicative inverse. If the first part of the algorithm fails, if we cannot get the verification that the GCD is equal to 1, then we stop, because there will not be a multiplicative inverse. Okay? So what we're going to look at now is how do we do the Euclidean algorithm, and then how do we do the extended Euclidean algorithm. So that's what we're looking at now. The Euclidean algorithm uses repeated integer division to determine GCD of a pair of integers. So we would like to compute this GCD. What is the greatest common factor, greatest common divisor of 5,889 and 6,513? So what we're going to do is we're going to divide the larger number by the smaller number and record the remainder. So when I divide 5889 into 6513, I get 624. That's my answer. And then what I'm going to do in the next step is this number moves to the inside, this number moves up. So I'm going to divide 624 into 5889. That goes 9 times. I take away 5,616. That leaves a remainder of 273. Then this number goes to the right. This number comes up. And I divide 273 into 624. So we're going to try this again. This goes twice. Let's see. 27 times 27 is 54, 546. 14 minus 6 is 8. 11 minus 4 is 7. All right. So then 273 goes to the right. 78 comes up. We're going to try this again. This goes in 3 times now. 8 times 3 is 24. 7 times 3 is 21 and the 2. 273 minus 234 is 39. 39 goes into 78 twice with 0 left over. We repeat until the remainder is 0. We eventually will get a 0. And the previous number is the GCD. The last non-zero remainder is the GCD. And so the GCD of these two numbers is 39, and it's not equal to 1. So 5,889 and 6,513 are not relatively prime. That's what this example tells us. Okay. The last non-zero remainder we found is a GCD. That's what we just did. Okay. So let's talk about the extended Euclidean algorithm again. Suppose that we do have a GCD, a GCD of 1. That means that the two integers are relatively prime. Then A has a multiplicative inverse mod n. The extended Euclidean algorithm returns that inverse. So here's what we want to do. We want to determine the inverse of 7 in Z mod 26. So the first thing we're going to do is just a regular Euclidean algorithm. This will go quickly because 7 and 26 are pretty small. I'm going to divide 7 into 26. That goes 3 times, and there's 5 left over. Then I'll divide 5 into 7. That goes 1 time, and now there's 2 left over. I'll divide 2 into 5. And that gives me 2 with 1 left over. And then I divide 1 goes into 2. And that goes in twice with 0 left over. And the last non-zero answer is the GCD. So that part is correct. We can perform the extended Euclidean algorithm. Okay? So that's what we did here. We divided 7 into 26. We divided 5 into 7, 2 into 5, and 1 into 2. And in the process, we got these three quotients, 3, 1, 2, and 2. So I want to show you where they are up here. They're right here, 3, 1, 2, and 2. I'm labeling these Q1 through Q4. You don't have to label them, but these numbers are part of the extended part of the algorithm. Okay? In the next step, we're going to seed the algorithm with a 0 and a 1. Where the 0 is kind of by itself, and the 1 matches up with the 3. Okay? And what we're going to do is we're going to repeat this step here. We're going to take the number that we have up here minus the product of the two numbers to the right. So 0 minus 3 is negative 3, and that's going to be the next number that goes up here. All right, so then the next number is going to be, we're going to start with a 1, and we're going to subtract the product here. 1 minus the product of negative 3 and 1 is negative 3. And 1 minus a negative 3 is 4. So that's the next number in the sequence. Then we're going to take negative 3 and subtract the product of 4 and 2, which is 8. Negative 3 minus 8 is negative 11. Okay? And I don't have to keep going. Once I have a number over my last quotient, I can stop. So I don't have to calculate 4 minus a negative 22. I finished with a negative 11. So the numbers that are came up here with 0, 1, negative 3, 4, and negative 11 are these numbers right here. 0, 1, negative 3, 4, and negative 11. We always start with 0 and 1. And the next k value is equal to the k value. So ki plus 2, which is here, is ki, which is over here, minus the product ki times qi, ki plus 1 times qi plus 1, which is these two here. This formula is confusing, I think, to remember, but if you remember the pattern, you know how to do it. Anyway, the final answer we got is negative 11, but negative 11 is the same as positive 15 mod 26. Those numbers are in the same column because if I add 26 to negative 11, I get 15. And so 15 is the multiplicative inverse of 7. Question here is, how can we verify this? We can multiply them together. 15 times 7 is 105. And 105 minus 104 is equal to 1. And 104 is 26 times 4. So if we subtract 26 4 times, we end up down in equal to 1. And so 105 and 1 are in the same column, mod 26. 4 rows apart, but they're in the same column. Okay? So that's the extended Euclidean algorithm. Let's do one more example. Let's compute the inverse of 17 in Z mod 26. So we start with the Euclidean algorithm. 17 goes into 26 one time with 9 left over. 9 goes into 17 one time with 8 left over. 8 goes into 9 one time with 1 left over. And then 1 goes into 8 times with 0 left over. The last non-zero entry is the GCD. So these numbers are relatively prime. 17 and 26 are relatively prime. And that means we can continue the algorithm and find the GCD. We start with the extended part of the algorithm, always with a 0 and a 1. The 0 floats out by itself so that everything lines up correctly. And we subtract the product from 0. So 0 minus 1 is equal to negative 1. 0 minus 1. Then the next thing we want to calculate is 1 minus the product here. So 1 minus negative 1 is 2. Then the next thing we want to do is negative 1 minus the product. Negative 1 minus a 2 is negative 3. And once we finish the row, that's the answer we want, but it's too small. Negative 3 is less than 0. That's an underflow. So we add 26 to it. And that gives me 23. And so the inverse of 17 is 23. Okay? That's how we do the extended Euclidean algorithm. Practice doing a few examples by hand. In a little while, I'm going to ask you to code this algorithm. So you'll want to be able to do some work with this algorithm and be able to use it to compute the inverse of some fairly large numbers. 17 and 26 are small enough numbers that we can brute force these kinds of problems. We're going to try some cryptographic problems where the numbers are too large to brute force, and you'll need some computer assistance to do this. Okay? So over the next couple of weeks, the first coding assignment is going to be to code these algorithms. All right. So let's take a look at a crypto system which uses the Euclidean algorithm. This is called the Affine Cipher. Alice wants to send Bob the message, "Rescue underway," using an Affine Cipher. In order to do this, she and Bob have to agree on two values, A and B. They both have to be in Z mod 26, and A has to be relatively prime to 26. So B does not have to be. So she could choose A equals 23 and B is equal to 6, and then Bob has to know these values. So Alice is going to convert each letter of the message to a value between 0 and 25, and then she will compute this value mod 26, AX plus B, or in this case, 23X plus 6. And that will get us the encrypted version of the letter X. Let's see how that works. So she takes the message, "Rescue underway," converts every letter into a number, and then calculates 23X plus 6 for each letter. In almost every case, this is going to end up being an overflow. This is going to be bigger than 26. And so she's going to have to subtract multiples of 26 to get these back down to something that's between 0 and 26. When she does that, these are the values that she gets. Let's just work through the first one, for example. 23 times 18. 3 times 8 is 24. 2 times 8 is 16. And then 23 times 1 is 23. That gives us 414 plus 6 is 420. But that's equivalent to 4 because 420 minus 4 is 416. And 26 goes evenly into 416. Goes once with 15 left over, and then goes 6 times with none left over. And so if we subtract 16 multiples of 26 from 420, we get 4. And that's equal to the letter D. We don't want to do all that by hand, and that's one of the reasons we'll be encoding some of this later on. But this is the idea. In order to decode the message, Bob first wants to undo this operation. The encrypted version of X is 23x plus 6. He wants to get his x back, and so the decrypted version of x, he would like to first subtract off that 6, and then ideally he'd like to divide by 23, but you're not allowed to divide in this system, and so instead he has to multiply by 23 inverse, and that's where the Euclidean algorithm comes in. So what we're going to do now is find the multiplicative inverse of 23, and then decipher the first two characters of that message. So if you've been paying attention, you know what the inverse of 23 is, because we did this problem in reverse a moment ago. But 23 goes into 26 once. 3 goes into 23 7 times, with 2 left over. 2 goes into 3 once, with 1 left over, and 1 goes into 2 twice, with 0 left over. That's the GCD. And so then we begin the extended part of the algorithm. 0 minus this product is a negative 1. 1 minus this product is an 8. Negative 1 minus this product is a negative 9. Negative 9 is an underflow. And so we have to add 26. And we get 17. That's the inverse of 23. And so that's going to be the operation that Bob does. 17 times x minus 6. So let's look at the first two characters of the message. We're not going to do them all, but we're going to start with the first two letters. They were D and Q. D is a 4, Q is a 17. So Bob wants to compute 17 times 4 minus 6 and 17 times 7 minus 6. This is 17 times negative 2, which is negative 34. That's an underflow. And in fact, Bob has to add 26 twice, because adding 26 to negative 34 will still give me a negative number. Bob has to add 52 to take this into the range from 0 to 25. Negative 34 plus 52 is an 18, which is the letter R. So if we do 17 times 17 minus 6, sorry about that. So 17 minus 6 is 11. That's 187. That's an overflow. 187 minus 182, which is 26 times 7, is 5, and 5 is the letter E. And so that's the first two letters in the word rescue, and Bob is now on the way to being able to decipher this message. Okay? So let's formally define this crypto system. What are P, C, K, E, and D for? So P is the set of integers mod 26, and so is C. We're taking numbers in Z mod 26. We're calculating something that converts them into Z mod 26. K is a set of all possible keys, but a key for this cipher has two parts. The multiplier, the A in the problem, which is relatively prime to 26, and then the number that we're adding, which doesn't have to be relatively prime to 26. So K is the set A, B, where A is in Z mod 26 and is relatively prime to 26. And B is just in Z mod 26. But it doesn't have to be relatively prime to 26. All right. E, the encryption functions are for whatever key, and a key consists of a pair A and B, it will be equal to A times X plus B. And then the decryption codes for each key is we're going to first off subtract B, and then we're going to multiply by A inverse. And I should say this is mod 26 in both cases. And those are the rules for this crypto system. All right. What is the size of this key space? So the size of the key space is the possible pairs of A and B. There are 26 possible values for B. But there are only 12 possible values for A. No even number is relatively prime to 26 because they both have a 2 in common. And of the odd numbers, 13 is not relatively prime to 26 because they have a 13 in common. So that leaves 12 possible values for A. And so the number of keys that Oscar would have to try if he wanted to break this by brute force is 12 times 26, which is 312 keys. Okay. We have this symbol here. This is the Greek letter phi. And in this case, it equals 12. It's the number of positive integers less than 26 that are relatively prime to 26. This number will show up in some of our calculations because of the invertibility of these numbers. This function has a name. I mean, the symbol is the letter phi, but the entire function is called Euler's totient function. Looks like the word quotient, but with a T. And some people just call it Euler's phi function. Or either one. We'll use this notation again later on, so I want people to see this. And so in Z mod n, this number is phi of n, this number is n. There are phi of n times n keys is what goes on here. And this problem turns out to be 312, which makes this more secure than the shift cipher, and at least in terms of just brute forcing, it's much, much less secure than the substitution cipher. What strategies could Oscar employ that would be more effective than brute force? So some of the ones he mentioned on the website for breaking the substitution cipher was to look at, for example, the frequency of certain kinds of letters. If we go back and look at Alice's encrypted message, I see that the letter Q shows up 3 different times in that message. Shows up here, and here, and here. And so I would guess that Q converts back into something that's relatively common. I don't know for sure what it is, but the fact that it turns out to be an E doesn't surprise me. It would surprise me if it turned out to be a J. So even though the size of the key space could be somewhat large, Oscar could strategize this by using letter frequencies again. Okay? All right. Have a fantastic weekend. I will see some of you in person on Monday, but there will be a video on Monday for everybody. Have a good weekend. Take care.